In the last video, we looked at choosing a sample size to meet a precision target. In this video, we're going to look at choosing a sample size to meet a power target. We're going to use the same experiment that we used in the last video, so the one with the jumping spiders and the females either choosing a male from their own species or a male from another species. And last time we were thinking about what could happen if the population proportion P, which represents the proportion of times the female chooses the male from its own species, we thought about the situation where P was equal to 0.5. In this video though, we're going to think about what could happen if that population proportion P was not equal to 0.5. So as an example, let's suppose that P was actually equal to 0.7. So if we were to run this experiment and we had data from sampled from a population where P was actually equal to 0.7, if we did a binomial test for P for that sample, we would expect to reject the null hypothesis that says the population proportion is equal to 0.5. And so in particular, if we were to look at the p-value for that binomial test, we would expect to get a small p-value that would allow us to reject that null hypothesis. So that's basically what we're going to do here. We're going to imagine that scenario and randomly sample some data that fits that scenario and have a look at the p-value for that binomial test. Okay, so let's make this a little more concrete. Let's imagine first of all that the sample size was 20. Let's set P equal to 0.7 and let's take a sample from that population where P is equal to 0.7. And then let's count the number of times that the female chooses a male from her own species. So in this sample, 12 times out of 20, the female chose a male from her own species, and 8 times out of 20, she chose a male from another species. Let's apply the binomial test to that data, and let's look at the p-value. So in this case, we got a p-value of 0.50. So if we were to do a binomial test here, we would not reject the null hypothesis because the p-value is bigger than a significance level of 0.05. So this would be an incorrect conclusion because we know in this case that P is not equal to 0.5. P is equal to 0.7. So this is a bad outcome. What we would like is a small p-value here. Okay, so that's just one random sample. Let's do this a bunch of times to see if we can see the patterns of what's going on, because we can't base any decisions on just one random sample here when we're trying to set up an experiment and figure out a suitable sample size. So let's do that 100 times. So same as before, I'll just set up an empty vector to store the results, and then I'll run the steps that we just went through 100 times, and then this is the result. So 35% of the time we got a p-value that would have allowed us to reject the null hypothesis. So in other words, a p-value less than 0.05. Okay, that's not good enough. What we're calculating here is what's known as the power of the test. The power is defined as the probability of rejecting a false null hypothesis. Okay, so that's what this number is here. This is the proportion of times that we rejected the null hypothesis when we did this sampling, and that's the power, and it's not good enough. We really want a power up around at least 0.8. So we're going to have to increase the sample size to be able to get a power of 0.8. So let's go to 30, say, and try this again. So let's see. I think I just need to run this part again. Yeah, there we go. So that's good. Higher power, which is to be expected, because if we increase the sample size and everything else stays the same, we would expect that the power would go up. But it's still not quite as high as I'd like it to be. I'd like it to be 0.8. Let's go to 40 and try it again. Oh, we actually did a little worse there. So these are random samples. So there's sampling variation in here, and so n equal 40 didn't seem to do it. Let's go to 50. Looks like maybe 50 is going to do it. Although I can't guarantee it because, like I say, we've got a little bit of randomness in the whole system here. Oh, thank goodness for that. Okay, we got a power bigger than 0.8 with a sample size of 50. Okay, so if you were going to go ahead and run this experiment now, and if you were thinking that the population proportion, let me back up. If you were running this experiment and you wanted to be able to detect when the population proportion was 0.7, if you wanted to have a power of 0.8 to be able to do that, then you really need to have a sample of at least 50 to have sufficient power for the test. Okay, so that's how to choose a sample size to meet a power target. So in this video and in the last video, we've been thinking about some fairly simple scenarios where we could actually do some sampling ourselves to choose a sample size to either meet a precision target or a power target. So this is quite challenging to do this, and in more complicated experiments, doing all these steps, it involves a lot of careful thought and consideration and some careful coding as well. And a lot of people have trouble with loops, so it's not for the faint-hearted to embark on this kind of analysis. Fortunately, in R, there are a bunch of functions that have been written and collected together into packages that we can use to do sample size calculations and power calculations. And so that's what I'll focus on in the next video. I'll show you how to use some of those functions to be able to do this kind of planning for sample sizes a little more easily than having to kind of go through all this fairly detailed coding. It's useful to go through all this though, because it helps you see what those power tools are doing kind of behind the scenes. So this is a useful exercise to have gone through to understand a little more deeply what's going on when you're doing sample size planning.